All right. Okay. So I think we can get started now. So people, when they join, they can catch us along the way. So we started this session last week, and we stopped at uh, one of the algorithms called KNN, K-nearest neighbor algorithm, and that is where we stopped last week. So before we continue, let's just give a recap of what we discussed last week for the first 5 minutes, and we can continue from where. So the chapter 2 is basically talking about supervised machine learning. As we know, supervised machine learning divided at the basic level, we have supervised and unsupervised, but in some other book, you can see many more, like not only supervised and unsupervised. But what we are doing now here in this level, we are saying they are divided into, for example, you may see reinforcement learning. Yeah. So, but at this level, we are saying machine learning is divided into two, but we also made distinction between what is machine learning, what is deep learning, because some people may not know what deep learning is. So deep learning is basically a subset of machine learning. And what we say, what is the difference mainly between machine learning and deep learning is that machine learning, given a data, we extract features, and now we work on the features and to do, for example, the classification. But for deep learning, you just give the algorithm, the neural networks, the whole data set, and the deep learning algorithm will figure it out on itself, which is somehow looks like magic. You don't tell it, these are the features that make someone a six, these are the features that makes this is a car. You just give the machine learning and the deep learning neural network the bunch of data, and it will learn itself. That is why sometimes deep learning algorithms they are called some kind of future learning. So they just learn the future on themselves. So that is what we mean by that, and we discuss. So this is where we discuss supervised learning is where like we have like training our machine learning, given the example and the answer, given example and answer, and the machine learning learn from that. And we say basically machine learning, supervised learning is divided into regression and classification. Regression is like predicting in continuous value, and classification predicting in two classes, for example, class cold and hot. So that's what we discuss. And but we also say that classification can also be divided into two: binary classification and multi-class. Binary is when you are dividing into two classes, and multi-class, multiple classes. That's what we discuss. We also discuss a concept called generalization, which is basically a concept in which we use when machine learning model learn very well. We said that the machine learning algorithm generalize well. So our intention is always to try to find an algorithm that generalize. If we said your model does not generalize, it means your model is not good. It does not actually, it does maybe good on training set, but it does not do good in test set. That we can say the model doesn't generalize. So our own aim always is trying to find an algorithm that always generalize on both training set and what test set. But we also discussed about the concept of overfitting and underfitting, where we said these are the two biggest issues for machine learning. And underfitting is overfitting is a situation whereby the algorithm is too optimistic on the training set, but it failed to generalize on test sets. That is that is what we call overfitting. But underfitting is what we mean by underfitting is that the algorithm does not even perform well on the data. Right. So we also say that there is a relationship between the model complexity and the data size. The more complex your model is, the more the more data you need. If you are using more complex model, then you need more data, because a complex model will fit the data set very well, perfectly in the training. But when it comes to the test set, it will not fit very well. So there is kind of trade-off between the using model complexity and the size of the data. And so we explained that we're going to use some of the data set that we use, some of the toy example data set, which are somehow called synthetic data set, meaning the data set I made up just as to do some kind of example. The first one we said is the forge data set. This is how we can download load the data set XY-mglearn, and this mglearn is a package that is being done solely for this book. So we may not bother a lot about learning a lot, but we just use it for the purpose of this book, so that because you will not see it in your real life machine learning. And we also say that, okay, there is also another data set that will be used, which is, we also discuss what is scatter plot and when we use scatter plot. We also discuss what is high dimension and low dimension data set. But also another data set that we'll be using in example is Wisconsin's data set. And this is how we can load data sets from scikit-learn, because we said a scikit-learn has inbuilt data sets that can be used for learning. So one of the data set inbuilt in scikit-learn is breast cancer data set, and this is how you can load the data set from sklearn. From data set, you can import data set, and you create an object, and this is your data set. So basically, this is what we discussed last week, and we said, okay, we will use these data set, one of them, to start learning one of the algorithm, which is KNN nearest neighbor. So this is a brief of what we did last week. Any question before we continue now?
All right, sorry, mine is not a question, but how about what we agreed to discuss last week?
Yes, so what we agreed to discuss is to meet 30 minutes before the session. And I was around 30 minutes before the session, only 2 persons attended, were joined. And we said, okay, maybe people actually forgot, maybe we can start the next session. Yeah, that's what happened. Do you join 30 minutes before the session?
Yes, I did actually, but what I realized is before I click on OK to enter the class, you ended the meeting.
Ah, okay.
Mm-hmm.
Right. So, okay, I want to ask question also. Does anyone have any issue regarding the installation or how you can run them? Because from now on, what I will be expecting of, like, after we finish this session, all of us will try to run machine learning algorithms to see that they run on their system. So if you have problem installation or something is running on your computer, then please set up so that we can, yeah. So some people like, this is BS code. I really like the BS code in the sense that you can do a lot with it. So that's why we are using. So a lot of people install BS code. They are using it. So let's go on to try to start doing the machine learning. So this is machine learning algorithm. So previously we just discussed a lot of things, but what we do is now the KNN algorithm, or called nearest neighbor. So when we have n, and n is called n, but when we say k nearest neighbor, sometimes you can hear that this algorithm is called KNN. It means k nearest neighbors. What k means in this algorithm is what we always try to use. This is sometimes called hyperparameter or model parameter. So let's look at it. Now, the KN algorithm is simple algorithm. It assumes one thing, that similar things exist in close proximity. What this means is that if you have many objects in a space, then the closer, if I have X and I have another X1 that is closer to X1, then I can predict that that X1 that is closer to X is of the same class. So just like if things are closer together, then we can say they are in the same class. If they are far away, we can say they are not in the same class. That is how KNN works. It just classifies a data point based on its pure nearest neighbors. So we call it neighbor. When we say neighbor, we mean something that is close to you. But the question comes, how many neighbor can we say that falls into the same class? So this is what we need to decide. So for example, we can see here, if we have this object and we have many neighbors here. So when we say we have only one neighbor, then we can say this thing is in the same class with this because it is closer to it. That is, we have one neighbor. So that is why you can see neighbor is equals to 1. So, but when we say a neighbor is 2, it means we make decision based on the 2 closest items, right? So this is what we mean. Let's look at what does that mean. So it can be used to solve both classification and regulation. So don't forget, the KNN, not only KNN, but a lot of algorithms can be used to solve both a regression problem and classification problem. So KNN can be used for that. So for example, KNN now can be used for sentiment classification to say something is positive or something is negative, or to say for hate classification to say something is hate or is not hate. But also KNN can be used to predict, for example, salary of university staff, because it can be used for regression. So that is it. But one thing is, how can we determine the distance? Okay, if this is the object and we want to know which class it belongs, how can we determine the distance here? How can we determine the distance between here and here? It means we need a concept of distance. What I mean by a concept of distance, I mean, we need to find a way to measure the distance between this point and this point. That is another thing. So there are many, there are many distance measurement, but one of the distance measurement that is widely used is Euclidean distance. We all know Euclidean distance in our mathematics, right? Euclidean distance, as we know. Let me see. Let's see. Okay. This Euclidean distance. Euclidean distance. Okay, let me put this. You can all see my browser, right?
Yes, sir.
Okay, so most popular distance metric used in KNN. For example, look at an example here. This one is talking about different kind of distance that are being used. So you can see. So you can see here, when we say we have k equals to 3, that is the neighbor. Can you see we have 3, 1, 2, 3, the neighbor? We can consider something like this. When we have k equals to 7, that is the neighbor. But how can we determine the, for example, this is a new example. So we have this example and we want to classify which class it belongs. Does it belong to the red class or does it belong to this class? Then if our k equals to 3, then we have this center. Then we will look at now what is the majority vote, because here we have the closer to 8, we have 2, which are this class B. Look at it, this is class B and this is class A. Now, this example, which class can we say it belongs to? Who can tell us?
It belongs to the green class, sir.
Yes, it belongs to class B. Why?
Because majority of the class B members.
Yes, exactly. Because the majority of the class B members are here. So this is basically what KNN does. So you think KNN is nothing like sophisticated algorithm, correct? It just, what it does is this, just intuition. When you are doing training for KNN, it will store all your location point of the training set. Now, for example, remove this one, which is the new example we are trying to do, but assume all these class A and class B, we train on them, then the KNN algorithm will just store this point will store them here. Now, when it store them, the algorithm, when it store them, then when you have a new example, then it will try to put the new example based on the point it belongs to. So for example, this new point, it belongs to this point. It may belong to this point. Now, when it belongs to this point, then we can now determine what are the neighbors it belongs. If our k is 3, if our k is 2, but what is the distance? How can we find the distance? So there are many distance metrics you can use. Many distance with their disadvantage and disadvantage. A lot of them, Euclidean distance, can you see it? Cosine distance, Jaccard distance. These are all distances that you can do. Hamming distance. So you can see these are all distances that you can be used to just I share this one that can be used just to find the distance of many points in your algorithm. But the good thing is when someone is doing research, like the machine learning research, so people will try to, let me come up with better distance algorithm. So people will just create another algorithm. This algorithm is better. But the simplest one we can use is just like we can use Euclidean distance, which we already know that just find the distance between these 2 points using this formula. So that is basically what distance is all about. So yeah, so we said you can see the using this, but building the model consists only of storing the training data set. Remember, KNN, I said, when you want to build a KNN algorithm, what you expect the algorithm, because what algorithm is doing is not computing anything. What you are doing is just like, you want to remember the position of the data point in the training set. So the algorithm will just remember all this position of the previous item. And when you have new data, it will try to compare, put it and find those data in your training set, the distance it has. That is what this means. Building a model consists only of storing the training data set. And now, how can we do this? Now, the KNN, what it does here is that it will tells you the probability of, it is not saying like, this belongs to class A, this belongs to class B. No, because what KNN does is it predicts the probability that this item is in this class B, or it predicts a probability that this item is. So it predicts probability that if probability is this, then in this class. So here we say class probabilities estimate for the new sample are calculated as proportion. What we mean by class probabilities? So we have two classes, class A and class B, and we'll have probability. The first probability may be if this is the probability it belongs to, it will belong to this class. It may belong. So we are using basically using probability to assign the classes. So yeah, so that is what basically KNN algorithm does. Any question before we continue?
Regarding the notebook files that you have shared last week, all
Yes.
the pictures that you have used as an example disappeared in those two files.
Okay. I will upload all the I will upload everything.
Okay.
Yeah, the folder for the
Okay, this is what I have realized.
Okay,
All
of
the pictures disappeared.
Yes, because I have, look at what happened.
Okay.
I share only this file, but the folder I supposed to share the folder. So here we have
the folder. Okay, that include all the pictures.
The images are here, so I only share this one. So yeah, I will share them. Yeah.
Okay, I understand. Okay,
right.
So thank you.
So that is what we KNN is all about. But there is one issue with KNN, and we will see that, which is called maybe scaling. Yeah. So what this means is that let's assume we are doing training, and our point here, they are of different scales. Okay, someone with question. Who raised question? Has question. Someone has question, right? Muhammad Hamza Alwa. You have question, Muhammad?
Sir,
Okay.
I want to ask a question, sir.
Yes.
So what I want to understand, in a situation whereby the nearest neighbor have equal distance, let's assume 0.5, 0.5, then how is the algorithm going to assign the classification, sir?
So he has a good question. When you have like this is 0.5, 0.5, what will happen? So I think here we make something like this. The new example predicted class is the class with the highest probability estimate. If two or more classes are tied for the highest estimate, then the tie is broken at random or by looking at it to the k+1 closest neighbor. So when we have a tie, the tie is broken at random. What we mean by the tie is broken at random is we look for another neighbor that is having distance which will not tie, or we look for another k+1 closest neighbor. We look another neighbor which is k+1. For example, your k is 2. Neighbor, you are looking for the neighbor, 2 neighbors, but you have a tie, then you can look for k+1 closest neighbor. Yeah, so that is how the ties work. But we also see example in this situation in the algorithm, then we can understand that data. There is something here that I want to explain, which is the concept of scaling, but we have not discussed that. But the issue is this. I think I can show an example maybe as scaling in KNN. Yeah. So yeah, this is another example. So why is scaling required in KNN and K-means? So why is scaling is required? So what is the thing is in KNN is this. You remember here, for example, here we have the age. Okay, here we have two data sets, age and income, right? Age and what? Income. Can you see it? And we can see that the age and the income is what? Large, right? But the age is very small, right? So when we are trying to find distances between age and this, then there will be some issues. So we need to scale the data into something that they have equal scales. We will discuss this one when we come. There is a concept for that, so that let me not confuse you. But I will discuss that when we come. So let's see an example, K-neighbors classification. So how can we do the classification? In its simplest version, we said KNN algorithm only consider one neighbor. So that is, yeah, so let's plot here. We just plot KNN. What we mean by this is a function. So you know this is a data set, right? MGLAN that we want to use, but this data set is just created. And this is a plot KNN. This is a function from scikit-learn that plot this kind of this for KNN algorithms. We have many functions that plot for various algorithms. So here we are just visualizing our data using one neighbor. So you can see this n neighbor is called hyperparameter or model parameters. So different algorithms, they have hyperparameters or model parameters. Hyperparameters or model parameters, we can tune it to make our algorithm learn better in our data set. So here we can see here, we have the neighbor is what 2. And we can see this is what it's trying to do. Yeah, we have neighbor 2. Now, you can consider any number and ranging not only 1, but 2, 3, 4. You can, but the question is, how many neighbors do we get better algorithm? That means when we have 1 n neighbor or 2, which case do we actually, our algorithm can give us a better result? Falalu has question. Go on.
Doctor, the sound is still very low.
Okay. Good. Good. Thank you. Falalu. What about now? It's low, right?
It's okay now.
It's okay. It's okay now.
Okay, it's okay now.
Yeah, it's okay now.
Okay. Yes, Falalu. Thank you for the. Yeah, I appreciate that. So the question is, it's not like we just assign the nearest neighbor for us to make decision randomly. There is something behind that. Who can help us? What do you think when we have n neighbor to be 1, our algorithm will be better? Or when we increase the neighbors, our algorithm, our decision will be better? What do you think? What do you think?
I think it would be better when we have more neighbors.
When we have more neighbors, you think the algorithm will make better prediction?
Yes, that's my thinking.
Okay. Anyone else as well?
Yeah, I share the same view with him.
Okay,
When we
so,
have more neighbors,
yes,
we may have better decisions.
Okay, so let's go on and see. So, but when we say like when considering more than one neighbor, we use voting to assign a level. What do you mean by this? So what we mean by this is like, for example, we are using 3 neighbors. So let me show you here. We are using 3 neighbors here. So when we are using 3 neighbors, this means that we are using 3 points to, so yeah. So for example, this is the new object and we have like, so here, what can we classify this new object? Which class does it belong? Who can tell us? Which class? So you can see we have the training. These are the training class, right? 0, training class 1. So this point, this red,
It belongs to training class 1, sir.
Yes, it belongs to training class 1. So you remember I said in KNN, all the training class, we store them. And when we have our test, so for example, this is test predict, this one. So when we have our test, then we compare it with the training class that we saw and see where the closer is. So here we have our k equals the neighbor is 3. Then we have you can see uneven. So we find out, okay, training class 1 is 2 and training class 0 is 1. So it means it belongs to training class 1 because it is. So this is what they mean by here. All right. So now we understand the theory of KNN, and let's go and see how we can actually apply KNN algorithm. So maybe someone can help us to explain these steps. Who can explain what we are doing here? Falalu, can you explain what this section is doing?
Okay, the first line.
Yeah, the first line.
So the first line, we have circuit plan package. Under it, we have sub-package model selection. So from it, we import the training test split function.
All right. Okay. So who can tell us what this second line does now? Saadatu, can you tell us what this second line does?
The second line, we have our X and Y variables. We are using the MG-LAN in the second line.
Okay, right. So basically this MG-LAN is a data set as we have seen it. It's basically a data set that was created mainly for this packet, for this book. And it has a data set. So here we are loading the data set MG4, called MG4. So here you can see this is a packet MG-LAN, and inside MG-LAN we have data sets, and inside data set, which data set are we loading? Make Forge, right? And you remember this is the data is synthetic data set, so it was just meant for. So what this is doing is assigning into X and Y. What is our X here means? What is our X? So if we run this, who can tell us what is our X now? What is our X?
On which example?
Sorry?
Based on which example? Oh,
yeah.
X, we said X is a independent, Y is a dependent.
Exactly,
But,
correct. Yes. So X here are so here each row like this is examples, right? Or we can send them an instance, right? So what is Y now here? If you look at them here, Y will be like a kind of value. What is Y now here is the target, correct? So you can see that here Y is the target. So here we have our X, the X and Y, and here we want to divide our data set first into trend set, test set, and stuff like that, right? And you remember we use this function trend test split from scikit-learn to actually divide our data sets into trend set and test set and stuff like that. And you can see here, the first thing we impute in our function, as you know, is the here the second one should be the target variable, and here you should be the future, right? So here we say the random state is 0. Random state means it's not we need, if we are coming back, we will generate the same data. Yeah, so that is this step. Do we all understand this? Anybody with question here?
Yes, sir. Please, if you can repeat first line and second line again so that we understand better, sir.
Right. So here is called from sklearn model selection, import this. So what we want to do now is we want to train KNN algorithms, but in the machine learning steps, we have many steps we said. The first one, we make the prepare your problem, what you want to do. The second one is to get your data. Now, we want to get a data. So what we want to do, the first step, as I made mention in our machine learning step, is prepare your data, correct? Let me do this. Maybe we can come back here. Frame the problem, right? Number 2, prepare your data or get the data, right? Get the data. We can also prepare the data. Prepare the data. So now here we already we already got the data here. Therefore, the problem we are trying to do is classification. We wanted to classify points into two classes. And how do we get the data? This step we get the data, because this function, this package mglan has a data set inbuilt in it. We are not reading a data set from CSV file, as we have seen in previous example. This package has a data come in it. So for purposes of these examples, but when you are doing real life machine learning, maybe you may read CSV data from your computer. So here we are reading a data set, and that data set, what it will return the future variable, and it will return the target. So whatever this mg return, it will assign the first one to x, and it will assign the whatever it return the second value, it assigned to y. So that is mglan, what mglan is. So here the first one here is from scikit-learn model selection. We are importing what is called trend test split. Now, when we have our data set, we want to divide it into 4: train, x-train, and x-test, then y-train and y-test. We want to divide it into 4 classes. But what actually divide it, we have what is called trend test split, which is a function in scikit-learn. So let's see that one, train test split sklearn. We did this one already. Yeah. So this is a function in scikit-learn called from model. Can you see it? Scikit-learn model selection. So look at it, model selection. So inside model selection, we have different kind of functions. So you can see here we have splitter classes. What we mean by splitter classes are just classes that just split something. So we have different kind of them, but yeah, can you see them? Right? We have splitter functions as well, not classes, which is trend test split. They are under what you call splitter classes. They split your data sets. Can you see? But not classes. So here we have classes. Can you see that? But here, this is the main object, which is model selection, and we have model validation, cross validation, and stuff like that. We'll also see that. So this is what we are using. We said from model selection, sklearn model selection, from sklearn model selection. Then when you call this, then you say, give me trend test split. sklearn, you need for you to call this any of these functions. For you to call any of these functions trend test split, you need to start calling from beginning. sklearn, because it's the main stop under the model selection. Can you see that? Then what under model selection? Trend test split. If you want to use check CB, you do that. So that is the idea. We discussed this one. So that is why we say from sklearn. This is how in Python you do that. So we from sklearn.model selection import trend test split. And here we assign this. So, but here we are dividing our data set, we are splitting, and this is where we split. So model selection here, trend test split, you give arrays of what are arrays is basically your X and Y. X is the future, Y is the target, and you put the trend set and stuff like that. So this is basically what we are doing here. As you can see, we are providing the X and Y, but here you can see we didn't even impute how we are going to divide our data set into trend and test set. Now, who can help us now? You remember that the test set and split, we divide them into our preference, but here we didn't specify how we can split the data. So who can help us? What is happening here? What will be the training size? What will be the test size?
Yes, the training should be 75%. This is
okay, right. So you can see here, we said if none trend, if none test or trend size, if none, the value is set to the complete. Okay, no, if trend size, we didn't provide trend size, is also none, it will be set to 0.5. That is text size. Can you see that? If trend size is not provided, then test size will be 0.25, and automatically when test size is 0.25, then the trend size will be 0.1.
0.75.
Exactly. Yeah, 0.75. So here this means that we can say test size. This is still the sentence. Someone can say, okay, this is test size is equals to 0.25 and trend size. So you see, this is why I like the VS Code. You can see I can have suggestion while you are doing programming. It can suggest many things. So yeah, so not only it can suggest all the function in scikit-learn. For example, it suggests function stuff for PyTorch and all of them. So it's really good. So here will be 0.75. Can you see? So by default, how data is divided if you don't actually provide this one, this is how it is divided. So the test size will be 0.75, 0.25, and the trend size will be that. So here we divide that, and here we have our that. Now, basically, when we divide our data, what can we do? Now, we are ready to train our machine learning algorithm. We have our train side and we have our test sides, right? So when you have your training side and test side, what do you need to do? Then you need to select the machine learning algorithm you want to train. The next thing machine learning algorithm want to train, we said, is k-nearest neighbor. But before you use k-nearest neighbor, you need to import that class from scikit-learn. So here also, before we use this function to divide our data, we import this from scikit-learn. In Python or in Python, if you want to use a function that is in another class, you first import the class. When you import the class, then it means the Python will be aware of everything, the function, the classes inside that. Now here we are importing from sklearn neighbors, import k-nearest neighbor. Can you see k-nearest neighbor, what it is? And can you see some examples here? This is a good feature, as I told you, for VS Code. So you can see here, you can see the explanation what KNN neighbors means. It will explain that. Not only that, it will even give you an example how you can use k-nearest neighbor. For example, you forget how you can use k-nearest neighbor or some stuff like that. You don't even need to browse your website. You need to browse in Google and find out, but you can just see, oh, okay, you need to import, you need to make an object, you need to fit, and you need to predict, and you need, can you see that? Can you see something like it? So this is actually what you can do with that. So yeah, so here, as I said, after you divide your training set, data set into train and test set, you need to train your model. But before we train your model, you need to import it and now create an object here. So here we call it import KNN. But here KNN neighbor, this class, you need to create a new object. We call it CLF or classifier CLF. And KNN, k-nearest neighbor, it has a hyperparameter, which is n neighbor. So here, inside here that we import, we can specify the neighbor we need. So maybe our n neighbor is 2. So now here we create an object. So this means that here we now train. Now here we feed the classifier using the training set. So here it means that we actually have our classifier now fit to this. Now we train this KNN using our train data. Yeah. So here you can see we have CLF, which is classifier. Now you can call the classifier and call this function fit. You provide the data. What will be here inside fit? It will be the X train and Y train. Always X train and Y train. That is, you are telling the machine learning algorithm, fit this. Wherever you see this, this is the answer. Wherever you see this, this is the answer, because X is the future and Y is the target, right? And the fit is what is actually doing the training. So here we say we fit the classifier using the training set. For k-nearest, this means storing the data, and so we can compute the neighbors during prediction. So here now it means we are storing the everything now in CLF classifier. Here you can name your variable anything, not only CLF. I'm just naming it here. So how can we make prediction? The next thing for you to make prediction is to call a function called predict, right? For you to call a predict is to make prediction. So here you can see that I have my the object that fit into my data. I can call predict. So you can see here the moment you create that object from this classifier, CLF, you fit on it. Can you see fit on it? And you predict on it. Can you see CLF predict on it? But when we are predicting here, we predict on test, X test, right? What does this mean? Who can tell us why we predict on X test? So here we said we fit. So this is what this is a called training step. We train our data. Fit, it means you train your data. In fitting, you provide the trains Y X train and Y train. Now here I'm doing predict. Why do I provide X test? Who can tell us?
Yes, I think the model is familiar with the training set.
Okay. Mm-hmm.
So the test set has not been seen by the model, so we use X test to know how the model.
Okay, so let me show you some. Okay, so yeah, so what we did here, let me see. Yes, question, go on. Go on. Question. Okay, go on. Question, right?
No, I just want to suggest something.
Yes, go on.
This question you are asking at the prediction, I think because at the prediction we are evaluating the model. Is that?
You say this question what?
That is. I said at the prediction state we are evaluating the model. That is why we have only the X test.
Yes, yes. So what we have here, we train the model, we feed the model, but we want to see does the model did anything good?
Works.
So
yes,
for us to train it to see whether it does good, we use X test, right? But how do we know that this answer it gives must correspond to what? Who can tell me this answer of the predict must correspond to what?
Y test.
Y test.
Yes.
Must correspond to what? Y test. This is okay. Let me see something here. Maybe I want to explain something. Okay. Remember, oh, no, listen. Remember, okay, don't assume there is no validation set here. Assume you have not seen validation set here. Assume we have only training set and test set. So here you remember we have X train, right? And we have what? Y what? Train, correct? And we have X test and we have what? X Y train, Y test, right? Remember in the previous slide where I gave an example, this section is called X train because we divide our data into two, right? Train size, this section, and test size. Assume this part for now. Assume it is all part of the above. This here is part of all of the above. Now we have X train and Y train. Now X train and Y train, we use it to train the model, right? Let's see it here. Can you see? We use it X train and Y train. We use it to train. We tell the model, if you see this in X and train, this is the result. If you see this, but now it means we have another two remaining section, which is Y train and what? Y test. I have X train and what? X test and Y what? Test. So now if I do training on X train and Y train, now I want to test my algorithm, then I will try the algorithm, try to predict on X test and see does it give me the same result in Y test? Do you understand the idea?
Yes.
Yes.
So we now train our machine learning model on X train and Y train. We say, okay, any point you see here, this is the answer. If you see this is the answer. Now we want to test it after it trained. Now we try to say, okay, we will try to predict, given X test, we try to predict the value here. Given any value, we try to predict. So when the prediction are the same, then we say our algorithm is really doing well. But when we do the prediction and but they are not the same with the Y test, then your algorithm is not doing well. Does that make sense? So you see, this is what we do when we are dividing our data set. Can you see that when we do the split, we have X train. Can you see it? And what? X test. And we have Y train and Y test. So it means these two are being used while doing what? Training. Correct? No. X train and what? Y train.
Y train, yes.
I use Y train. But X test is used to make prediction on. And when we make prediction and we will look at Y test, does that result in Y test the same as the prediction we did on X test? If they are the same, then we say our algorithm makes good prediction because the algorithm hasn't seen the Y test. Is that correct?
Yes.
So yeah, so that is what we did here. That is what we did here. We fit means we are training on X train and Y train. You are training here. Now we predict here using X test. Now it gives us this. Now let's go and find what is Y test. If we find Y test, the result of Y test is the same as this prediction, the Y prediction, what these guys return, which
X
is
test,
this,
yes.
then we say yes. So let's look at this is Y test. So when we run Y test, the output to output the same?
Yes. No.
Not
No, they are not.
exactly.
They
Yeah?
are not.
They are
They are
not.
not.
Exactly.
They are not.
But
They are not the same.
they are not okay. The first one is 1, right? Second one is
Yes.
0. Third one is 1, 0, 0, 1, 1,
Mhm.
0, 1,
Fifth one.
0, 0. But it's only one place that is not. It doesn't make correct
Yes.
prediction, right?
Yes. Yes.
Is this algorithm? Does it make good prediction or not?
Yes, it makes prediction.
Yes, it makes.
It makes, because remember the algorithm hasn't seen Y test. Now we just predict, given X test, we predict and tell us and say give us the corresponding Y of any of this. The algorithm say okay, these are the corresponding Ys. But now at the background I come as because I already, me as a person, I know the Y test. I now look at the Y. Okay, this is it. But yeah, so here I just compare this manually to look at what it doesn't make good, but this is not done in real life situation. When you make prediction to see your Y test, it's not done in that way. Do you understand? I just try for us to just see it. For example, when we have 1 million Y tests, are we going to try to look up 1 million one by one?
No, we cannot.
No. So we have, so this one I just use it just to show you what does that mean. So that we cannot do this for large data and go and check manually where the model is correct. So here you can see we check where the model is correct, where it's not correct. So to evaluate, this is how you can check your machine learning algorithm is doing good. You do your prediction. When you do your prediction, so for example here you train, the first step is train your algorithm. We train it here, make prediction. Here we make prediction. And now you evaluate the algorithm and try to find out whether the prediction is good or not. So we have many ways to make the prediction. So one way is what is called score in sklearn. Score is a function. Can you see what this score does? Return the mean accuracy on given test data and levels. It returns what is called mean accuracy. What do you mean by mean?
Sum of the accuracy and
Average.
divide by.
Exactly, average. Some of, yeah, excellent. Someone tell us some of the stuff and the bad. So you can see this CLF, which is our what we train on, then we call score on it. Then we give it the X test and the Y test. Now it will give us the score. You can see the score is 0.85. Oh no, I don't realize. Okay, we have not fitted it where. Yeah, okay, let's look fit it. Okay, he said we have not fit this one. Okay, we have fit it now. We make prediction now, and let's score it. You can see the answer. Can you see that? So now the accuracy of your classification is now 0.85, which for classification, this is a good accuracy. Very good. So to summarize, for you to make machine learning using sklearn is import your train set split, divide your data into train set, right? And import the algorithm you want to use. Here we want to use KNN's classifier, but KNN has many neighbors, many what do you call it? Many model parameters. You can set as small as possible you want, and you create your model to fit into the data. When you create this, then you feed the data. After you feed the data, then you predict, you make prediction. After prediction, then you what? Evaluate your model on score. This score is just making what we call a mean. So return the mean accuracy, which is classification metric. So we have many classification metrics, but for this one, we are looking at what is called a score. Now, this is what score is doing here is just returning the mean. So here we can see, okay, let me give an example what this score. Okay, now the score return values from 0 to 1. The score, when it is 1, it means your algorithm makes perfect prediction. When it's 0, then your algorithm doesn't learn anything. So score has a value from 0 to 1. But as I said, what score is doing is actually doing calculating the mean. So let me show you what score is doing. So this is y-predict that I showed here, y-predict, and let's look at the y-test, and this is the y-test, and we say, okay, it is only one place they didn't make correct result, right? Now, I can now try to find out where these places makes a good where these places make a correct prediction. Then you can count 1. So here I said y-pred equals to y-test. I'm trying to compare which place this is equal to this. So I have this is true. The first one is true. They are correct. They are the same. Second one, but it's only this where they are not the same. So how can you calculate this? So I have 1, 2, 3, 4, 5, 6, right? So
yes.
6 all over what? How many are there all?
6 over 7.
What is 6 over 7? Who can calculate 6 over 7?
0.
What is 6 over 7? What is 6 over 7?
0.857.
Yes, 0.8. You can see that is where we have our mean. Can you see? So here, this is, so instead of using score function, sometimes you will see that people may use mean. So here we are using a numpy mean function from numpy to calculate the mean.
Exactly the same.
Yeah, where this return result, where this is both for learning purpose, just show you what is really happening behind the scene. But what you can do is just use score. You don't need to know that. So just use score, give your X test and Y test, and call this one, and you see the accuracy. Yeah. Anyone with question?
Yes, please.
Yes.
I do have. Please, at what range would you consider that a score value is inappropriate? Is it probably below 70, below 60? You know, at what mark would you rate that?
Your question, are you asking like your accuracy at what percentage that you can say is good prediction or not?
Yes.
Okay.
Is there a specific range?
No. So it depends on your data set. Because, for example, if your task is so complex, you may not have a good accuracy. So, for example, now there are many factors. I think you cannot say that this is the, for example, the value in which you can say this is where something that has been benchmarked. It must be that. Yeah. So I think there is no, but the more beta algorithm you have several options. For example, now you learn all algorithms that you can do for the classification, and you try 10 of them. There is 10 of them, and you see the accuracy of each one. You can take it, but there is also, you can combine multiple algorithms, 1 and 2. That is what we call that way. We come to that makes a strong prediction better and then a single algorithm. Yeah, I don't think there is because like when you are writing also a paper, what you can do is like make a prediction and write the result and say this is our result that beat the previous result. So people will always try, when you are writing the paper, try to their algorithm or their work, make a prediction and come with accuracy better than the previous benchmark accuracy. Yeah. So yeah. So if you want to do some, yeah. So you try to I mean, yeah, a lot of ways to try to tune your algorithm to make better prediction. But yeah, also if your data set is so complex, you cannot actually say that I must read this accuracy, stuff like that. Yeah. But we expect that the algorithm should be like maybe more than 50%. When you have less than 50, it means even chances. So what is chance? Chance is 50%. So 50%, it means chances prediction. That is when we turn a coin, the chances is like 50%, right? So we expect our algorithm to be maybe somehow more than 50%. So it is worse than it is better than the chance cases. Do you understand what I mean?
Yes.
Yeah.
Right.
Yeah. So that is how we can train KNN. Any question? Any question? Right. So let's look at something here. We can say how we can analyze KNN. Here we said if we have two data sets, as we already said in previous session, you can use plot your data using what we call scatter plot, right? So here you remember the previous data set we work on has two points, that is x and y. So we can actually plot them. So here what we want to show is this. This here we have we want to plot k nearest neighbor with different n, with n equals to 1. You can see this one is with n equals to 1. This one with 3 neighbors. This one is 9 neighbors. So you can see here, I have 1, I have 3, and have 9. So we want to see when we have neighbor equals to 1, what will be the algorithm looks like. When we have neighbor equals to 3, what will the algorithm looks like. When we have neighbor equals to 9, what the algorithm looks like. So here we want to make some kind of generalization about the n number parameters of KNN. So you can see for k equals to n equals to 1, our algorithm try to fit the data very well, right? Try to fit. Can you see? Try to fit the data very, very well. Can you see that? Can you see when our k nearest neighbor is 1? Can you see the algorithm fit the data very well? But when neighbors is 3, you remember what we mean by neighbors? What we impute our KNN algorithm, this parameter, this one, where is it? Neighbor. Can you see this neighbor? So this is what I mean. So what is the effect of having k neighbor small number or neighbors large number? That is what we want to try to see. So you can see when we have the neighbor very small, 1 here, it try to create these separable lines and fit the data very well. Can you see that? What about this? When we have our neighbors equals to 3, can you see it try to separate the data? But it's not very well, right? But here, it tried to separate the data very smoothly when our neighbors here is 9. Now, which one is better here now? Who can tell us? Neighbor here is 1, neighbor is 3, neighbor is 9. Who can tell us?
I think 1 is the best.
1 is the best? Okay, because it separated our data set very well, correct?
Yes.
But remember, we are doing training here. It means now it fits the data very well when n neighbor is 1, is a very small number in training set. It overfit the data in training set when your neighbor is small. Remember what we discussed about overfitting and underfitting? Overfitting is when a training set, your data set is fitted very well. The algorithm learned the data very well at training, but failed to perform good on test sets. But here we are training, and our algorithm learned to fit the data very well, and the algorithm here may not perform very well here on test set.
Yes.
So what this is telling us is that, as you can see on the left in the figure, using a single neighbor result in a decision boundary. This is called decision boundary because it's making decision about which boundary, which class is it. So this is called decision boundary. So as you can see in the left hand figure, using a single neighbor result in a decision boundary that follow the training data closely. Can you see that? It divides the data closely. Considering more and more neighbors leads to a smoother decision boundary. But considering the more neighbors, can you see more neighbors like this, more neighbors like this? A smoother boundary corresponds to a simpler model. So remember this one. We talk about complex model in the previous session, and we talk about what? Simple model. A complex model is a model that will fit the data very well, correct?
Yes.
At training set, but may not fit the data at test set, unless we have more data.
More data.
Yes. So, but a simpler model here, this one is smoother here with large number of n neighbors correspond to simpler model. In other words, using few neighbors correspond to high model complexity, and using many neighbors correspond to low model complexity. So yeah, that is the problem. That is the issue. So when you have your n neighbor is 1, is low, then your model is very complex. It will try to fit the data very well on training set, but it may not fit the data on test set. Yeah, so we'll learn this more in the future. But as for you now, what you should know is that we should have like kind of the neighbor, n neighbor, to be somewhere between. We'll see something in the future, somewhere not smaller like 1, not large like n, somewhere average in between that can make decision much better. Oh, any question? So I have a question here. What is the influence of hyperparameter? So you see, now this hyperparameter, as you can see, since you said here at that example here I gave, you can see that when my k neighbor is like particular number, when the algorithm doesn't work well, I can change my n number, I can change my nearest neighbor until I see my algorithm works well, right? And on both test set and test set. But there is a problem here when tuning hyperparameter. So this is the problem here. Let me explain. This is very, so assume you want to train your machine learning algorithm. And now first you said your n neighbors is 2. And now, okay, you do the prediction on X test and see, oh, this does not work well. You say, I need to tune my parameter. You go and change your parameter to 3. You run the algorithm again, right? You run the algorithm again, run it, and oh, it doesn't work well. You also go and try to change this to 4. So you can see now the algorithm, you are trying to change it, but the algorithm is exposed to X test. We are showing the algorithm X test. Do you understand? It means X test is something that we should hold on, that the algorithm hasn't seen at all. It's when we finish everything. So it means now here, we need to have a different data set that will allow us to fine tune, to tune our algorithm. We iterate our algorithm, tune our algorithm. And when we finish our algorithm, we should have a separate data set that we haven't seen, we haven't shown to algorithm while tuning, that will test the final performance on that algorithm. Do you understand the point I want to make?
Yes.
The idea is this: we don't want to always show our algorithm the data we want to test its performance. But when we are tuning parameters, we already show our algorithm to predict, and we have this, we see the prediction is not correct, we iterate, we change the parameters. Now our test data is now exposed to even the algorithm. He will remember it. So this is a bad behavior. In that case, we need another data set in which we will actually be using while testing our algorithm, where we are changing our parameters. And when we finish everything, then we will test the final performance in a single data set. That brings us to what is called, now we need to divide our data sets into 3 classes. That is what is called train set, validation test, and test set. So you train your algorithm and you iterate on validation set. That is what we call model selection state. So here is model building. You are building your model. Here is model selection. You select the model that works well, and here you you evaluate your model. Does that make sense?
Yes, sir.
So if I understand you, you mean that we are going to try all the classifiers or what?
Yes, yes. So for example, you have even 10 classifiers. You can try your classifier on this training set and validate its performance. So for example, I have KNN, I have another support vector machine. I have different algorithms. I want to see their performance. You can train on this data set and look at the validate performance on this. But as I said, sometimes we change some parameters in our algorithm, right? Then you go back and change the parameters and change run your validation set. And when you find the validate, you will find the model, the criteria that bring best performance. Then you select this model. That is why here we say this data set is used for model selection. And now you finally test on your data. Yes, go on.
Okay, like that key that you change from 3 to 4 to something like that.
Mm-hmm.
Okay.
Yeah, so what I give this example, what we are trying to say is this. Here we are using only one example, which is KNN. What we are trying to say is this. Your algorithm prediction performance, as we have shown here, may depend also on some parameters of each algorithm. Different algorithms, they have different parameters. Then changing these parameters or tuning this parameter will change the accuracy of that algorithm. So for example, as we said here, let's say this one is like we have 28 neighbors. Now we run this and we fit it here. When we fit it, let's see, we predict here. What is happening? Okay. So here I change my n neighbors to be even greater than the sample data set I have. So that's will not work. So maybe let me say this one to be like 10. So your n neighbors, as you can see, must be less than the sample, example, the instances you have in your data set. So in my instances, I have less than 28, I think. And here I said that my neighbors is 28. So you can see you cannot find distance between less than 28 items. Do you understand?
Yes.
So yeah. So here, let me assume like my neighbor is 10. Let's look at, okay. And now let's make prediction. And we have this one. And let's find the accuracy score. Yeah, so here is still 0.85 something. It doesn't make any difference. Yeah, but what we are saying is, generally, because the data set is small, generally the performance differs from when you have different parameters. This parameter is for this algorithm, KNN. If you have different algorithms, they have different parameters. Now, okay, let me show you. Yeah, let's look at the parameters. Can you see KNN? What are the parameters? N neighbors. By default is 5 if you do not provide it. There is what is called weight. There is what is called algorithm. There is leaf size. There is P equals to metric the distance, Minkowski distance. By default is using Minkowski, not Euclidean distance. Metric param, N jobs. Can you see we have different parameters? Here we are talking about the simplest instances. So here you can change different parameters to make the algorithm to give better performance. Here I choose only one parameter, N neighbors. But don't bother about knowing all this one. What you can know them when you have like you can know them as long as you go on. But let's start from the beginning. We use only one. So here when you come here, you can put so you can see all the explanation of these parameters. Can you see that? So in a nutshell, what we are saying is like you can tune your model. So the good thing is now we are no longer divided. We will not be longer dividing our data sets into only train set and test set, but you can divide your data set into train set, validation set, and test set. But in this session, session, we will not divide the data set. We will continue into our using the train set and test set. But this thing, someone bring it up in the previous sessions that sometimes we divide our data set into 3 classes: train set, validation set, and test set. Yes, of course, that is why I showed this example. Any question before you continue?
Yes, I have a question.
Yes.
Yeah, it's about the validation set. So the validation set is where we do the model selection. So my question is, if we keep fine-tuning our model, won't it learn the validation set? Will it give us the accurate value there?
Okay. So when you do that, when it learn in validation set, when it learn here, you are not making decision that your algorithm works well on validation set. You are making decision model evaluation on your test set.
Okay, but from my understanding, the test set is supposed to be used at the end.
At the end. It means
after
so
evaluation.
now it means when it means now is that because there is a situation where we said oh, I forget that. Okay. What I'm trying to say is this. This is you are selecting a model. You are selecting a model. You are not evaluating it. So selecting a model is like you went to a field. You want a field. You want to play a football. You want to play a football. You put 3 players in them, and you ask them to play. In the first round, one performed well. In the second round, another performed well. In the third round, one didn't perform well. Then you select the one that performed better and try to go with it in a competition. Do you understand? So here you are just trying to train and select what works well, and you test it on, you evaluate it on different something that hasn't been seen. Yeah.
Okay.
All right. So that is actually the question. So any question before we continue? Yeah. So here we said let's start here this is another thing. Let us investigate whether we can confirm the connection between model complexity and generalization. So we want to confirm whether the complex model may be one with low n neighbors, like example 1 or 2. Does it generalize? Let's compare that. So here you can see we are going to use a real world data set, which is breed cancer. And we are loading it from sklearn. From sklearn, import load breed cancer. So this is how you can import the data set. And here we can see cancer, load breed cancer. And so here we have our data, which is cancer. And now here we train, we want to divide this data set into train, test, and size, right? So here we call our function train, test, split. We have our cancer data, cancer target. So here you can see this is a data set cancer. But when we say cancer data here, it will give us the future. When we say cancer, the target, it will give us the target variable. So you see that. So here, here also you can see we haven't specified the train size and test size, but it will be divided equally. And here we say stratified. We have the random stat. So here you can see we want to actually use KNN. We want to use KNN, but with different neighbors. The neighbors we are trying to use now is neighbors start from 1 to 11. Do you understand? We want to use KNN with neighbor 1, with neighbor 2, with neighbor 2, 3 up to 11, and see where what will happen. So right now we divide our data and we create now a simple create something empty array, which is called training accuracy and test accuracy. And now here we said we create another variable, neighbor settings, range is 11.1. What range 11.1 means? It includes 10, how many neighbors from 1 to 10, exactly, right? Because range is not exclusive, right? The 11 is not included in the range function. Is that correct?
Yes.
Yeah, so here it means I have values 11, 1 to 10. Yeah, can you see range stuff? Range object, range start and stop, right? Yeah, so what this means is that we are assigning this variable number, setting numbers between 1 to 10. Instead, so this is still the something like, instead for us to just say we want to specify like 1, number 1, 2, 3 up to. So this is how we use it to assign numbers. So now what we want to do is this. We are creating a for loop here, and we say, okay, for n neighbor, for n in n neighbors, that is for any number into n neighbors, and n neighbor setting is how many do we have? 10, from 1 to 10, right? Then for n to n neighbor, it starts from 1. From 1, it go back, it will select 2, it will go 3, it will go 5, 6, 7, 8, 9, 10, up to 10. This is for loop in Python, you should know. And now what we are doing here is, look at it. Our classifier, KNN classifier, n neighbor. So here, if for the first one, n neighbor is 1, 1 is assigned to n neighbors. Can you see that? We feed the training SVM. We train accuracy here. We have what is called train accuracy is empty, but we use append here. So here it means that this we created this one score, X train and Y train for the evaluation, remember, for the evaluation. And now the result is now appended, is input into this empty accuracy. Remember, this is dictionary, right? Do we know what this append means in Python?
Yes, it's concatenation.
I mean, do you know what this append means? What we are doing here?
Hello?
Do you know what we are doing here, Saminu?
No, actually, I just know the word appendix.
Okay. So what we have here is this. Our intention is this. Our intention here is we want to try to find out the accuracy of k nearest neighbor on training size and the accuracy of k nearest neighbor on test size, on test. But we want to use different n neighbors. So here we are actually trying to iterate through n neighbors, and here we are finding the accuracy, and the accuracy we are storing it in an empty
array.
Yes, here that we created. Append, it means store. So the first one, when n neighbor is 1, we calculate the score, we store. Now here is on train, and here on test. Here also we append on test accuracy, the empty one. Can you see that? Now we go back. Now for n equals to 2, because here is 10 numbers, for n equals to, it will do the same thing and store the result in this train accuracy and test accuracy. And now here what we do lastly, we just plot them. And here we plot the result. So what here is telling us is this. When we have the accuracy n neighbors, you remember we started from 1 to 10, and here is the accuracy. So for n neighbors, when it is small, this one is for training accuracy. So you can see here we have training accuracy that we are storing, training accuracy using X train and Y train, test accuracy on X test and Y test. Can you see that? So here is test accuracy, test, this is training accuracy. So this means that when we have n neighbors, it's small, the training accuracy is so perfect. Can you see it's 1? It means that when we have small n neighbor, the data on training size will fit very well, but it will perform poorly on what? Test size.
That is on the kitten.
Yes, exactly. That is so here you can see the data when we have our n neighbor is very slow, it's maybe 1. The data will perform very well on what? On training size, right? But it will perform poorly on test data. Can you see that? So, but this is also on test data at the date, and the accuracy you want to be always good is on test data. As you can see, also we are doing as on test data. As we increase the number of neighbors, you can see even on training side, as we increase the number of n neighbors, is decreasing.
The performance is
decreasing. Yes, but on test size, as you can see, we increase. It started to increase, but it started coming down. So it means that it's somewhere else here that at KNN n equals to maybe 6, the result is beta. Can you see?
That is, we get the
Yes.
optimal result at 6.
Optimal
Exactly.
solution, yes.
Somewhere, yeah. I don't know whether this is exactly 6 or something like that. So you can see. So considering single nearest neighbor, the prediction on the training set is perfect. But when more neighbors are considered, the model becomes simpler and the training accuracy drops. So one model, so the test accuracy for using a single neighbor is lower when more neighbors, indicating that using a single nearest neighbor leads to a model that is too complex. On the other hand, when considering 10 neighbors, the model is too simple and performs even worse. Can you see that? It's too simple. And we don't want a model that is too simple, right? We want a moderate model. The best performance is somewhere middle, using around 6 neighbors. Can you see that? So here, it's just an experiment trying to tell us n neighbors with smaller neighbors, n neighbor, the model is complex, but with maybe somewhere else it is better. So that is that. Let's run quickly and do the next one. We have a few minutes to finish. The next one is KNN for regression. So as I made mention previously that KNN can be used for both classification and regression. So what is the difference? How can we define it when we are doing regression? What can we do? So here we said there is also a regression variant of K nearest neighbor. And this is what we can do that. Okay, we will use a data set called MakeWeb in MGLand. Here we import the data set. I just show the data set here. You can see it has, this is the target, this is the future. It has 2 futures, I think. Let's look at how we can use the KNN for regression. So if you want to use KNN for regression, let me quickly, this is how you can do it. Let's understand this one. Remember, for classification, we say from cycle 9 neighbor import KNN classifier, right? But here we said K nearest neighbor regressor. We will import regressor. When we are doing classification, what did we import?
Classifier.
So we want to use regression, we import regressor. Now here, we will create our X and Y. Can you see we import our data set from MGLand and we assign to X and Y. So here, this is our future, this is our trend, right? Now the next thing is what? To divide our data into trends play, right? And here we input the X, which is future, and here is Y, which is what? Target. Now we divide our data set. What is next thing? The next thing is what? To create what?
A model.
Yeah, to create a model. How can we create a model? This, you call the KNN, K nearest neighbor regressor. In regression, we call KNN classifier, right? But here we can regressor, and you give the n neighbors. Shall we put 1 or 2 or 3? Which one? 1 is more complex. Somewhere we can put 3, right?
Let it be like 3 or 4.
Yes, something like that. So we leave it to 3 now here. And now after making your model, you fit, then we fit the model here. Is that correct?
Yes.
But we didn't specify the test size or training size of our model.
Yes. But if we do not provide the test size and train size and test size, it will automatically create a training size to be 0.25 and train size to be 75.
Okay, as it was stated in the documentation of train test.
Yes.
Okay, I got it.
So now here we fit it, and now here we predict. Can you see we predict here? Now, when we do okay, I didn't run this, I think. Okay, now we do that. Now here we predict. Now after predicting, what else remains? We evaluate our model. Is that correct?
Yes.
When we do prediction, the next one is we evaluate our model. Is that correct?
Yes.
So for regression, we are not using score, the one you know. We are using, anyway, just leave it, but you just call it a score. So here you can see we can call a score function. Our model, which is regression, I call a function called score, and I provide X test and what? Y test. Is that correct? Is that correct? Do you understand this?
Yes.
Do you understand this? Maybe let me remove this one as false, and maybe if it is confusing. So after making prediction, what else do we do next to evaluate our model?
Evaluate.
And evaluate our model, we use what? Score function. Is that correct?
Yes.
So here we use a score function. And now can you see it tells us it's 0.84, the accuracy, the score. So here this, what we calculated is, you can see it's like the accuracy is 0.83, but for regression, we use what is called R square, which is also something to find the regression accuracy, and it's quite good, which is 0.3. The result of R square is also 0 to 1. If you have 1, you mean your regression is very good. So I think we are good to go. Our time is up. Any questions? So we can see now that for you to do classification and regression using sklearn is more or less the same. What you need to do is just to change the top. If you are doing classification, you just import classifier. If you are doing regression, you say regression. Do we all understand? Any question before we go on? Any question? So,
yes, sir. Just a clarification.
Yes, go on.
I already installed VS Code initially.
Okay.
Later, when I heard about Anaconda being having all the packages, I went on and installed Anaconda again.
Okay.
So now I have both Anaconda and VS Code, but I want to remove one. So can I remove the VS Code and just
no, you don't need to remove. So Anaconda that you install Anaconda, it gives you all these packages installed. For example, scikit-learn, NumPy. But VS Code is just an environment where you can run. You don't need to, when you install VS Code, you need to install Anaconda again to have those packages already installed.
Okay, I get it.
You cannot use VS Code without installing those packages that Anaconda already installed for you.
Okay. Okay, it means now I can just be working with my VS Code, taking advantage of the packages.
Exactly. Yes, exactly.
I'm clear now. Thank you.
You need to do a kind of, give a kind of line of code that will connect the two, or
no. When you install Anaconda, or Miniconda, and you install VS Code, the moment you open VS Code and start typing, everything will work perfectly. You don't need to tell VS Code anything.
You don't have to call any.
No. Okay. But when you install VS Code, you need to come here and you install Python, because VS Code is a kind of a tool that can use for many programs, any programming language, C++, anyone. But when you install VS Code, now you come here and install Python. So when you need to install this one, Python and Python, you need to install this Python. You can see it here, right? Python is already installed. So you need to install this package called Python, and maybe Python Intellisense. So the one that is showing me something like this, when I put this, it will show me like something it's called Python Intellisense. So I think it's here. Why is Python Intellisense? Not Python. Right. Let me. Python. So if you install it, I think when you install this one, will install the Python Intellisense automatically as well. So when you install this one, for you to use VS Code, what you need is only this: install Anaconda or Miniconda, install VS Code, and now install Python from here. So let me show you this. this is what you need to follow. Data science with BS code. So if you come here, they explain detail how you can use BS code. So for example, the prerequisite for use BS code, install BS code. When you install BS code, install Python extension. This is what I was telling you. Python extension and Python Jupyter extension. So these ones, you need to install them from extension marketplace. So in BS code, this is called marketplace. You can install everything you want. For example, I want to use C++. I can install C++. Can you see? I can install C++ so that I will be using C++ in BS code. But I want to use only Python. Just install Python. When you install Python, everything will work. So you can see here, you need to install this extension, which is Python, and you install Miniconda. You remember, so if you already install Anaconda, you are fine. But Miniconda, if you install VS Code, before you use VS Code, you use Python VS Code, you need to install Miniconda, because Miniconda will automatically install packages for you like Pandas, Jupyter, Seaborn, Scikit-learn, Keras, TensorFlow, Miniconda. Miniconda is somehow kind of small version of Anaconda. Anaconda is bigger package. You understand, there are something that you don't need, but at the lowest level you can install. So when you install Miniconda, then you can just start doing some stuff like this. Can you see that you can start doing your? So this one explain how you can.
Please, can you drop the link for us so that we can?
Yes, I share the link in the chat as well. Yep. So.
Shamsu.
Yes.
Even though this is just the beginning, but I wanted to ask,
yes,
with regard to this regression algorithms.
Yes.
Why is it most of the papers that when they did prediction for this regression algorithm, they usually report the accuracy. They are not reporting the predicted value.
Yeah.
Why is it that the predicted value is not always reported? They always report the accuracy just to compare to.
Good question. So this is what we want at all, Mustafa. We don't want when we are doing machine learning, we don't want to. Let me open this thing. So when we are doing machine learning, this is what we want. What we want is this. We will not report the prediction. This one, no. What we report is the score. The score, that is the accuracy of the machine learning. So here I use maybe KNN. It gives me 0.834. Maybe I use support vector machine. It gives you 0.93. I use in the paper. You will not report anything. Only this one. You say, this algorithm give me this accuracy. This algorithm give me accuracy. Then you select. You tell them which algorithm works best in your data set. Yes. So that way you can so for example in Kaggle competition, in Kaggle competition is environment where we use machine learning. So when you do Kaggle, what you submit in Kaggle, millions of people are doing Kaggle, and millions of people are for example competing and getting a lot of money. But when you go to Kaggle, what people are submitting, for example, you can see here $150,000, $100, $75,000. These are all competition. When you do your, they will give you data set and try to make prediction. And what you will submit is only the score. It's only the result. Do you understand? It's only the result. So they will give you trend set and test set. Do you understand? And you try to do prediction and stuff like that. And what you will be evaluated based on your results. But you will not submit this prediction and stuff like that. Yeah.
Okay. But will the algorithm, produce a predicted value? Because in a situation where you are not comparing any algorithm, maybe you wanted to use only one algorithm just to make a prediction and get the value. Maybe you wanted to use that prediction value, predicted value for your own research. Would that be possible?
Yes. So if you are not interested in, so always when we want to do machine learning, we want to always try to choose the algorithm that give us the best result. Is that correct?
Yeah.
So in that case, if you are not,
because there are many papers that already perform they already compare different.
Yes,
algorithms.
exactly.
Exactly. So you can choose the best one.
Exactly. So in the literature now, because we are just starting, we are not saying this one is the best one or not, but in the literature, as we go on, we will know that. So in practice, people are not even using KNN because it's so simple and it does not support large number of features. Do you understand? So we will all know this stuff as we go on, because like it will make us decision which kind of algorithm we select to do our machine learning. Yeah, that is correct, Mustafa.
Okay, thank you very much.
Any question? All right. I think what we should do is that please try to run in your computer up to this stage. Try to do regression. Try to do it yourself. If you have problem, you cannot do it. Follow the example in the book. I will also share this one. If you cannot do it, or you have issue, just let us know in the Slack, and we can help you to do that. Yeah. All right.
Will you share this notebook today?
Oh yeah, so I can share the notebook as well today.
Oh, okay. So thank you.
All right. Okay. Thank you.
We'll try as much as possible. Okay. So
thank you. Bye bye.